So among the things we're going to discuss today are introducing a new type of sensor. We've talked a lot about resistive-based temperature sensor, and we've developed examples based on that. Perhaps you're kind of wondering, surely there must be more, right, than that to biomedical instrumentation, and there is. The reason I haven't emphasized it until now is many of the principles that we're going to be learning about apply to anything you want to measure, right? And so as you're learning things like voltage divider and maximizing your output voltage, it doesn't matter what you're measuring. But of course, at some point it does, right? Now, as a reminder, we have this sort of picture of an instrument with some sort of circuit, a couple wires going here, our sensor, and of course, our display. Okay. And as we've gone through the course, what this means is starting to make more and more sense to you. Now, the thing we're measuring is called the measurand. Up to now, we thought about something like temperature, right? And it's the measurand that the sensor picks up. So for example, if you have a resistance that is a function of temperature, right, that then starts to cascade, right? And hopefully this concept now is very, very obvious. Yes? Yes? Nothing? Okay. But what about measuring something else? So to do that, I want to first start by thinking about a resistor as an object. So let's imagine a resistor, and let's intentionally, I'm going to draw it as a tube. We're going to draw it really big. Right? So here are the wires that come out on either end. Right? And it is a three-dimensional object, right? It's a real, is this still around here? Floating around? No. It's a real object, right? And we're used to think of this as having a certain resistance in ohms associated with it. And we already discussed that what it's made out of has a very profound effect on the overall resistance, whether it's made out of copper or plastic, right, will matter as well. But it turns out the shape of it matters as well. And that's given by this equation. So we're going to say that the resistance in ohms is equal to something that it's made out of. And we're going to call this the resistivity. And this will have units of ohms, let's say ohms centimeters. Become clear in a second. This relates to what it's made out of, times the length this quantity here. I'm going to put a little L. The length of it divided all divided by the area. So I'm going to add units here, centimeters squared. And by area, I'm referring to this. So we can use, let's say, capital A. And so we can rewrite this using a Greek symbol for resistivity. I'll leave the units up. Times L in centimeters over the area in centimeters. And you can see how the units work out, right? So that we end up with ohms, right? And that's why, that's from a unit perspective, why this had to be ohm centimeters. What does this equation tell us? It tells us that, first of all, the resistance is directly proportional to what it's made out of in terms of this quantity called resistivity. So copper has a low resistivity, and plastic has a high resistivity. All right? But you also need to be aware of the size. The longer it is, the higher the resistance. So even once you've decided you're using some sort of material, you still need to know its dimensions, such as its length. And once again, it's proportional. So if this marker has a resistance of 10 ohms, 2 markers has a resistance of 20 ohms, right? And 3 would have 30 ohms. So as we make it longer, we actually increase the resistance. Now that may not be so unintuitive. I mean, what if we were to think of this as a 10 ohm resistor and this is a 10 ohm resistor and we put them head to tail? Well, we would have 10 plus 10 is 20, right? So now what we're doing is we're combining it into one. But it turns out that the area also matters. But here, the bigger the area, the smaller the resistance. There is more space for electrons to flow through. Now, one good or bad analogy for resistance could be flow through a pipe. And I heard this about analogies. Analogies are as good as they're useful to you as an analogy. So if this analogy doesn't work for you, it's not going to help, right? But if you can imagine, if it's useful for you to think of this as flow through a pipe, and the pipe has some resistance, right, to the pressure applied across it, as the pipe gets longer, right, that resistance is going to increase. But as the pipe gets bigger, that resistance will decrease. And so this tells us how to think of a resistor as an object. It's not that complicated of an equation, I think, right? There's just 3 terms and we're sticking to algebra, right? You have to take your resistivity, you have to know your length, and you have to know your area. Now, typically when you are getting resistors, like in your circuits component, they don't rely on these other elements. Usually not. A 1 mega ohm resistor, right, is not a million times longer than a 1 ohm resistor. That wouldn't make any sense. So you can imagine that usually when you're at the circuits factory, you're really relying on resistivity, right? And then the length and the area, though, have to be factors as well. So far, so good? Okay. Now, when you have a resistor whose resistance changes with temperature, right, what would be your guess of what's changing? Which of these do you think would be changing? You have a 1 out of 3 chance of guessing, yeah. Which one? The length, maybe. So as the temperature increases, maybe it changes its shape. That's actually quite possible. That's usually not the dominant term. What else? But it's a good guess. What else? You want to guess the area? So again, you're thinking that it just swells. Also, not a bad guess. But it's not the primary one, but good guesses. So we're left with resistivity. All right, we're left with resistivity. But you were absolutely, what you said is very prescient, because I'm about to show you when these things do matter. So it wasn't a bad guess. But for most resistive temperature sensors, the main effect is resistivity. So in this case, the resistivity is a function of temperature, meaning the material properties themselves are a function of temperature. And you can see, for example, that if going from 25, well, let's write it out. If going from 25 degrees to 30 degrees, right, C, were to change resistivity, and we'll do this in ohms meter, from 10 ohms centimeter to 20 ohms centimeter, right? Then the resulting resistance, right, would also double, right? If this quantity doubles, right, then this quantity doubles. If this quantity reduces by 10%, so did this one. So there's a very proportional relationship. Even if these things are fixed, there's a very direct relationship. And so we can see how the resistivity, the material property, what it's made out of, changing with temperature, will therefore change the overall resistance. So far, so good? Okay. All right, so having introduced resistance as sort of a product, thinking about resistors, right, as physical things, that have these components, right? I now want to introduce something called potentiometers as a sensor, and particularly a sensor of motion. I want you to imagine a situation like this. I'm going to take a resistor, and I'm deliberately drawing it long. So it goes on and on and on. Now, does a resistor, the resistor doesn't actually wiggle like that, right? But you know, it has a border, but this is the resistor. I'm going to measure the resistance from this point. Let's say I measure it to this point right here. All right, so this location, which is location number 1, and this distance here happens to be, we'll make it it's 1 centimeter. And I measure here a resistance of, we're just going to make it simple, a resistance at 1 centimeter of 1 ohm. Why do I measure 1 ohm? Well, it's a function of the distance, but also of the area, right, which I've been given you in the material properties. Now, I'm now going to move this needle 1 centimeter down to a new location, so that now the total displacement from start to finish is 2 centimeters. At this point, the resistance I measure at 2 centimeters will be, well, what has changed here if we think of this as a physical thing? Did what it's made out of change? No. And this didn't change, but this changed, right? And specifically, it doubled, right? So what will happen to the resistance? 2 ohms. And let's use the full spectrum of colors here. If I were to go on all the way here, and let's say at its full length, it's 10 centimeters. So I would get that the resistance at 10, it's obviously not proportional here. What would be the resistance at 10 centimeters? Yeah, not a trick question. It would be 10 ohms, right? Not a trick question, 10 ohms. And so that's all the way here. So what you can see here is that as we slide this needle along, we are changing the resistance just according to this equation. So far, so good? Now, of course, I could turn it the other way around. I could say, right, and this was our third position here, just to be clear, right? And this was our second position. Now I could turn the situation around and I can say, all right, I'm sliding this along, but I'm not sure where I have it. But I stopped at a certain point and I measured 2 ohm. Do you know what position it's at? You do. You would say, oh, it's at 2 centimeters. So I can go from position to resistance. So the resistance here is a function of, let's just say, position. Position. And in fact, as I've drawn it here, there's a pretty simple equation for it, right? That would say that the resistance is equal to the position in centimeters times 1, I made it very simple, 1 ohm per centimeter. That's it. This is a resistive position sensor. Just like this was a resistive temperature sensor, we now have a position sensor. And we're using the same principle here, right? Only now it's not this that we're focusing on, it's this element that we're focusing on. Let's say you wanted to make a device that would measure Someone had a stroke and they can't move their arm very well, right? And you want to measure, you want to make this a bit of an abstract example, but you want to measure a device where you measure how far they can move their hand, right? You maybe do something like this and you measure it and they're moving their hand back and forth, right? So you need to make a position measuring device, right? You fix them initially at a certain point and you ask them to move their hand as far as you can. This is how you would do it. And you can see why I wanted to start the discussion here with resistors as objects. Because once you start thinking about resistors as objects, you really understand resistive sensors in general, because if any of these change, right, you have something based here, right? Now, they actually make potentiometers. I should make this. Probably, if you're going to make a practical device to measure position, I don't think you would do it this way. We'll talk about other ways to do it, but it's a nice place to start. They, in fact, make linear potentiometers. It would look sort of like this. There's usually like a little track that goes on the inside. And then there is a like a handle that goes inside the track. And then on the ends, you have sort of points to measure the resistance. What is happening is essentially something that looks like, effectively looks like this on the inside of it. So you can buy one of these sort of dials, right? And so this would be a linear potentiometer. Let's imagine another situation. I'll try to draw it carefully, where we put a resistor. Yeah. You get the idea, right? It's like the resistor goes in a circle, right? And we will insert a dial here. And the dial can be displaced to different positions, right? And this dial can, and we will measure the resistance R, and I'm going to put a thing here as a function of angle, between this point here, and if we imagine this dial is conductive, and this point here. So, as we start in this position, we're not measuring much at all. It's like a short, and then we're measuring some resistance, more resistance, more resistance, more resistance, right? As the dial moves, you'll measure more and more resistance. It is the same thing as moving the dial in this way, but it's just kind of rotating around. And so again, we're moving it around to different positions, and we have an angle here, and the resistance that we measure will be a function of the angle that we're moving through. And so from the outside, it might look like just like a can like this. And I'm going to try to draw this as like a three-dimensional knob that you can rotate. And then here are where you measure the resistance, right? This is a more typical form of potentiometer that you would see. Now, in conventional electrical engineering, this is used when you need to put a resistor in your circuit, but you're not sure what that resistance should be. Okay, and there's examples of that where you need to load it in, but you're not sure if it should be 10 ohm or 11 ohm, and so you put this in instead, and then you can trim the resistance later. But in our case, you can see that this could be converted into an angular motion sensor. Someone is disabled, and they can't bend their arm very much, and you want to create a device where you can measure whether they can bend their arm 10 degrees, right, or 45 degrees, or 90 degrees, right? So again, I don't think practically you would necessarily do it this way, but if you had to, you could imagine attaching their arm to this pivot point, right, and making sure that as their arm moves, this rotates along with it, right? Angular displacement, linear displacement. It is still a resistive sensor. And you can see that what you measure happens here. Right, what you measure happens here. Now, what circuit would you connect this to, right? What would be the next step here? Any guesses? There's two circuits we've taught. Either one would work, but let's pick one, yeah.
I would use an LED. Because, like, as you turn the potentiometer,
Yes.
that light goes higher or lower.
So the suggestion was to use an LED. I think you're already thinking like the next step. What before even then? Well, I mean, if you connected this just to an LED, the LED would never light up, right? Because there's no voltage source, right? So you're thinking a step ahead. So what circuit would you connect this to? What's that? A Wheatstone bridge? More sophisticated answer, good, you could. A more sophisticated answer I'm looking for, even more basic answer is the voltage divider, right? I'm actually happy we actually went through these other examples because it's very useful. So we're going to connect this, and let's draw it here. Here's once again our voltage divider circuit. We're going to have a battery source. Let's use an example of just going head straight and attaching it to 10 volts. Let's go ahead and use a fixed resistor. I'm just going to give it a value for now. Let's say it's going to be 100 ohms, right? And right here, is our R position. Just squeeze that in there, okay? We're going to measure the voltage, call it VP for position, from here to here. And now we have, of course, as always, VP is equal to, I'll just abbreviate this as RP, R sub P, R sub P over R sub P plus, in this case, 100 ohms times 10 volts. All right? That is our voltage divider equation, right? Now in hot pink, all right? And we also know that R sub P depends on position according to this equation, right? So let's just write that here, that R sub P is equal to this displacement, this thing we're calling position. Well, it's times 1 ohm per, we'll just write it here. 1 ohm per centimeter. Now, look what we have here. We have two equations. One equation is for the sensor, and the second equation is for the circuit. And I've emphasized that in this course, you're going to see the same things repeated so much that it will become, I don't always say boring, annoying. You're going to see the same things over and over again. And I say no matter what instrument we make, you will see two equations. One equation is for the sensor, and one equation is for the circuit, right? And in design, you sort of maybe start here and then go here, but in interpretation, right, you would record your V sub P, right? This is measured, right? To make sure this is measured here, you measure this, right? And then you would work backward. Let's do a quick example like in our head, all right? In our head, all right? And I'm going to pick simple numbers so we can go through it in our head. Let's say you measure a VP of 5 volts. All right, so there's 5 volts here. At this point, you may have enough intuition with voltage dividers to know that if you start with 10 and you have 5 volts here, it means 5 volts here, right? Because it's an even voltage division. And so this resistance is what? What would this resistance be to give you 5 volts here, an even split? $100 ohms, right? If this is 100 ohms and this is 100 ohms, right, then we take this 10 volts and we split it evenly, right? So I know we're doing this in our head, right? So that's why I was saying if you see 5 volts here, that tells me that it's 100 ohms. But you could have also gone through this equation, you would have found the same thing. So now we know that RP is 100 ohms. But what's the position? Now we go to our second equation, which is, it's almost so simple, it's confusing. I realize that, right? But it's a very simple equation, right? We have 100 ohms, right? What's the position? It is 100 centimeters, which I know is more than what I've drawn here, right? And if you think about it, that is the same exercise we did for temperature, right? Whether it was a thermoresistor or a thermistor, it's the same thing. Yes?
So in this case, how do you visualize the position? Is it that the resistor is 100 centimeters long, or that's like...
Yes, in the illustration here, but of course it doesn't have to be this way, right? I could have, for example, made, yes, it would have been 100, to do this example, which is why I don't think you'd quite implement it this way, you would have to imagine that there's 100 centimeters, right? A meter, it's like a meter long wire, just the way the numbers worked out. Again, in practice, if you go online and buy a position sensor or like something like that, I don't think you're going to see, it's not going to be used for this purpose, but it is good conceptually. So far, so good. So lo and behold, after weeks of biomedical instrumentation, you have finally moved beyond temperature sensor, right? You now know how to measure temperature, but you also know how to measure position, right? Distance and position, right? But now look what you get for free. Now look at what you get for free. So if you're measuring my position, right, and I move, right, in 1 second I move a centimeter, and then another second I move another centimeter, and another second I move another centimeter. So you measured my position once, my position twice, and my position again, right? You measured my position time 0, you measured my position at time 1 second, and you measured my position at time 2 seconds, and so on, right? What do you now have? You're measuring position over time, right? The position, be clear here, this was time, so we had 1 second, 2 seconds, 3 seconds. I didn't say what position it was, but we had a position measurement here. So you can see that my position is moving. What can you extract from the slope of this line? I put numbers on it. I'm going to say 1 centimeter, 2 centimeters, 3 centimeters. So in 1 second, I moved 1 centimeter. Another second, I moved. What is it that you can extract from this? Constant positive slope, exactly, which corresponds to? What's another word for that slope? What's that? It's linearity. I'm even looking for something simpler. You guys are thinking ahead. Yes. What is linear over time? The rate of change of distance, which is velocity. Yeah. I'm sorry, it was such a simple question, you may not realize what I was asking for. Velocity. What I'm trying to show you is that if you have position and you're willing to measure at one point and then another point and another point, you have velocity. So you have now temperature, displacement, right? Linear or angular. And now you know how to measure the velocity of something. Maybe in a slightly awkward way because it's attached to a potentiometer. But if you had to measure, so there's some child and they're impaired, and you need to measure how quickly they can move their hand forward or back, you could use something like this, right? They're slow, they're quick. And the same thing would go for angular, right? So, okay, we've quickly moved beyond temperature. I've given you displacement. I've given you velocity. Anything else you think you can get for free in that same theme? Position, velocity, yeah, acceleration. So if instead of this, you saw this, and then this, right? So the slope of the slope, right, is going to be acceleration. So now, look how quickly we're going now. We were stuck in temperature for so long. Now I've given you displacement, motion. I've given you velocity. I've given you acceleration, right? And maybe now that you have acceleration, you're thinking about maybe something else, right? That you'll be able to extract from acceleration. maybe if we put like a mass on this, so instead of being freely moving, there was a mass, right? And we could go on and on, all right? But if you want to know where you want it to start, I need you to start here. And as long as you got this, right, you can get to displacement, right, velocity, acceleration, and so on. Does that make sense? And how are you doing it? With a voltage divider, right? Now, of course, you have to do this calculation, which is where we are now in the class, right? We're not doing that digitally. And if you want velocity or acceleration, you're going to have to measure it at multiple time points, right? And do the calculation yourself. That process can also be automated, of course. So far, so good.